A plus UR minus this part. This part is the displacement of atom R minus 1, so UR minus 1. Okay, so now I have the distance between atom UR and UR plus 1 equal to this one, as well as UR and atom UR minus 1, which is this one. Okay, so now by using Hooke's law, the restoring force on atom R is the mu UR plus 1 minus UR minus mu UR minus UR minus 1. So now, at first, the distance between R and R plus 1 was A, R and R minus 1 was A, right? But now, the distance between R and R plus 1 is equal to this equation, and R and R minus 1 equal to this equation. So now, you want to know what is the spring force depth acting on this atom. So we use the force, the Hooke's constant, F equal to negative Kf, but you want to know what is the difference between these two, between this and this. So we know that what this difference. So we got U mu UR plus 1 minus UR, the first distance minus the second distance. Okay, then time the Hooke's constant, then you get F. Then from this equation, we can simply rewrite into this one, okay, by just doing some very simple mathematical calculation. So now we have two restoring force. Okay, the first restoring force we obtain from this one, okay, F equal to ma. Then the second restoring force we obtain from F equal to negative Kf. Okay, so now we want to compare these two restoring force, 9.3 the first one, 9.4 the second one. So when we compare comparing these two restoring force, we have F equal to ma equal to F equal to negative Kf, or F equal to mu x. Okay, then you rearrange this equation. Then you move the m to the right hand side. You move the mu r, ur to the left right hand side, negative to the right hand side. Rearrange it, you will get this equation 9.5. Okay, so based on equation 9.5, this one, you want to further simplify it. Okay, we know that the equation for mu ur and ur plus 1 as well as ur minus 1. Okay, this is the equation for ur. Oh, not this one. Correct. This is the equation for ur. Sorry. This is the equation for ur. So when you want to get ur plus 1, then it's a plus 1. Here it's just plus 1 lah. So substitute into here, substitute into here, substitute into here. Then you solve everything. Then you will get this equation. Then this equation. Then this equation. Okay. In the early of my teaching for this subject, I will just show the student, okay, from here to here to here. But I found that some of the students not able to solve this type of the mathematics due to the relatively weak in the mathematics background. So I have actually also prepared the step here, so you can actually refer this slide for how to get from this equation to this final equation. Okay, I'm not necessary to provide you all the steps for the later equation, but for the earlier one, yeah, I will provide you the solution lah. Okay, so from when we compare the equation from f equal to ma and f equal to negative kf, then eventually you will get omega square equal to blah blah blah. Okay, if you don't know how to get this equation, you can refer to this slide lah. Okay, so if you are viewing the video recording, then you can just pause and then look at the solution here. All right. So therefore, the dispersion relation for the longitudinal wave. Longitudinal means that in only one direction, and the movement of the wave is same with the movement of the lattice vibration, because the movement of the wave is along x direction, and the atom or the lattice vibration, like the lattice, also vibrate in along x direction. So this is what we call the longitudinal. If the atom vibrate in x direction, but then the wave is along z or along y direction, then we don't call it longitudinal. Okay, we call it transverse. Okay, come back to this equation. So from this equation, we found that omega square equal to 4 mu over m sine square Ka over 2. So we can say that we have found the relationship between omega and K, and what control the relationship between omega and K. So here I have a few parameter. A, the Armstrong, not the Armstrong, the lattice constant, and then the mu is a Hooke constant. This Hooke constant rely on the type of chemical binding. Okay, if the chemical binding like covalent ionic is very strong, then of course this mu will be stronger. If it's just like the very big one, the van der Waals and then the hydrogen bond, then this mu also smaller. And then as well as the mass of the atom. Okay, so remember at the beginning of this course, I have asked a few questions what actually control the relationship between omega and K. So now we know that from this equation, the A, the lattice constant, the mu, the type of the chemical binding that you have studied in previous chapter, and the mass of the atom control the relationship between omega and K, and we call this type of relationship dispersion relation. Okay, then omega equal to blah blah. Then you also get omega equal to this one. Okay, when you square of it both sides. So this positive negative represent the wave traveling to the right or to the left, because wave can travel in left direction and as well as right direction, doesn't matter. So when positive then right, negative then left. So this is the omega max. Omega max, this is the amplitude. Okay, so omega maximum, this is the maximum of the omega that you can reach. So in other words, you can also see here, right? This sine something, the maximum is 1. So that's why omega equal to omega max when this is maximum lah. So this is maximum. So next, I think you have studied in 106 if not mistaken, the group